K is a 1. What's it going to do? Reset. That means take it to a 0. But it already was a 0, right? So does it change? No. It stays 0, and we keep that going out like that. Everybody okay?
Can you go over that again, please?
You have to look at this edge. What are the J and the K inputs? The J is what Q naught is doing, and that's a 0. And this guy is a 1. So it's got a 0, 1 going into it. You clock it. It says reset. It already was a 0. It just stays a 0. Yeah.
So you take a value just before
Just
the time frame.
before.
And
Nanoseconds before.
the fact that the two clocking inputs are wired together, that just means they're both operating on the same.
Exactly the
Okay.
same clock. Now, we could certainly have different clocks, but most of the time you don't. Is that okay? What's going to happen next? Okay, we're going to look at this clock time here, correct? What is J1 or J naught?
0.
0. What is the K1?
1.
So what's it going to do?
0.
It's going to reset. It was a 0, it's now going to go to, or it was a 1, it's going to reset to a 0. Yes? What are the inputs on this guy here? Okay, just before the clocking event, this was what?
1.
1. What's this guy? 0. What's it going to do? It's going to go to a 1. It is set, correct? What you should notice here is that this is a shift register. Where have we come up in your BME life with shift registers?
To even out signals. Like,
Yeah, just give me a course.
All of the above.
288, yeah. 288, right? So we talked about shift registers and how we can use these guys to make memory, or well, we were using for low-pass filters and other type of filters. There it was an integer that went into a cell. Here it's a binary number, correct? But we've made a shift register by doing this. What do you suppose would happen if I put a few more JK flip-flops out there? You get more memory cells, correct? Yeah. Okay, so what I have got here is I have the capability of making a shift register where I can store numbers.
Dr. Brown, one more question for you.
Mhm.
If the clock was not wired to the second gate, then the inputs or the output from the first gate would directly go into the second gate.
Say that one more time.
So if the clock was not wired to the second gate, it was only wired to the first gate. When we have it wired like this, if we get Q naught to be a 0, but it was a 1 beforehand, we still use that 1.
Well,
If the clock was not wired to the second one, you would use whatever output you got, and it would just be like cascaded gates.
well, but remember, we have to clock the second one with something.
Okay. Okay.
Otherwise, it's not going to do anything. It has to see a clocking signal.
Okay.
Are we ever going to see ones that are on different clocking
Yeah, look at
ways?
your homework problem.
Can we do an example of one that are on two different? Okay.
Take a look at the homework problem.
Asking the important questions here.
What What are every last one of the J's and the K's? What are they? They're tied where? And then just tell me what values are every last J and K. Are we looking at the same flip-flop? Every last J and K is tied where? DDD. DDD. Yes.
I'm crazy.
DDD. And what is DDD? It's the power supply. What do we consider the power supply? Logic level 0 or logic level 1? 1. Every last one of those is in what state then? The toggle state. Yes? So you notice that what's happening is that the Q is going into the clock of the next one. Okay. So you ought to be able to figure out what this thing is doing. Okay. And it's got a name up on top of it. It ought to tell you what it's doing. You just got to verify. Okay. What's it called? It's a 4-bit up count. Count form. There's 4 bits. Start counting.
0, 0, 0, 1.
Add 1. Add 1. Add 1. Add 1. Add 1. Add 1. Add 1. Counting is very important, right, for timing issues. Okay. When you buy a computer, what's one of the things that you look at in terms of deciding whether you're going to get that computer? The speed of the thing, clock speed, okay, which in your case is probably up to what, a couple gigabytes, gigahertz, right? We like everything inside our machines to be clocked so that there's no race conditions, etc. So, 2 billion times a second, these things, all the guts in there are being clocked. We just showed a clocking pulse. That clocking frequency is going to be up there at the 2 billion hertz range. Questions at all? Okay, the top one is trying to have you figure out what kind of a gate that is. So just as a review, if you have a NAND gate, the gate to source voltage is high. Is the gate on or off? You were very positive about that, but you're wrong. A NAND gate to source voltage high, the gate is on. And therefore, what resistance? 400 ohms for our logic level devices, right? We can get FETs that will have on resistances down in the milliohm range, okay, but they're much, much bigger devices. Okay, gate to source voltage 0, what's the device? On or off? Off, and therefore we model it as a
Open circuit.
PMOS. Source to gate voltage is a 1, it is on. And we model it as a 400 ohm resistor. Source to gate voltage 0, off. Model as an open circuit. Okay, once again, when you've got these gates like this, Okay, this is our invert gate. This is what kind of a device up here? PMOS. Where's its source and drain and gate? I'll give you the easy one, that's the gate. Where's the source? Source is at the top, it's always associated with the arrow, correct? This is the drain, how about this guy? Drain, this guy. Okay, now, a little bit different nomenclature on these guys here. They're using, instead of a configuration like that, it's showing like this, and this guy on the P channel is coming out. But again, source up there, drain down there, again, PMOS, and drain source for the NMOS down there. So you just got to figure out how to make the transcription between the two different settings. Everybody all right with that? Okay, so the source is always at the top for the PMOS, the source is always at the bottom. All right, kept you way too long. Tune in on Monday.